I am Dr. Y.D. Dwivedhi, Professor from Institute of Aeronautical Engineering, Hyderabad, India. I am in the continuation of my course, Aircraft Stability and Control. Today I am in lecture number 16. The topic of this lecture is Trim at Airplane Cruise. In the process of learning of aircraft stability and control, previously we have covered some topics related to aircraft stability, the effect of wing, effect of tail, effect of fuselage, effect of engine in the stability of the aircraft. We have seen that the basic role of the wing is to produce the lift. However, most of the time, the aerodynamic center of the wing is falling ahead of the center of gravity. This location of aerodynamic center and the center of gravity makes the wing unstable in static condition and it making the aircraft nose up. To counter this phenomena, we need to use one horizontal tail which is far behind to the center of gravity of the aircraft so that the leverage can be obtained, and by the less amount of lift force generated by the horizontal tail, we can counter the moment generated by the lift. So, the most of the time the horizontal tail is used to counter the longitudinal moment which is generated by the wing. In the process of this, we have to go for further the trimming condition, and in today's topic I am going to discuss about introduction and revision, aircraft aerodynamic center, problem and solution on aerodynamic center, then trim condition, elevator position, stability requirement, and explanation of static stability. These points I am going to cover in today's lecture. As we have seen, this is the diagram of a F-15B for the lift coefficient, that is the CL, and in horizontal axis, that is x-axis, we have the angle of attack. Angle of attack is ranging from 0 to 90 and coefficient of lift is ranging from 0 to 1.6 or 1.8. Here in this plot, we can see the effect of horizontal tail, that is angle of horizontal tail, the basic setting of horizontal tail angle, that is IH, that is incidence angle of horizontal tail. One is 0 degree, another is minus 15 degree. Then we have the minus 30 degree, and then we have the plus 15 degree. Once we talk about this incidence of the horizontal tail, so this is the horizontal tail, and if we make the positive, means this leading edge should be upward like this. If it is like this, it is a positive, and if it is like this, the leading edge is towards the bottom side, or it is nose of this is going down, then it is a negative. So in this case, we have to see that if we change this angle, the setting angle of the horizontal tail, what is happening? So these are the results which are obtained from the wind tunnel of F-15B fighter aircraft, and you can see a very interesting results that At 0 degree, this you can see the coefficient of lift is quite less. Means if it is like this, it is approximately 0 degree. Here, this you can see the first plot here. This first plot, it is ranging from here at minus, at 0 degree, you are getting the minus 0.2. And as you increase the angle of attack, somewhere at nearly 25 degree angle of attack, you will get here. This is the value, and here this you can see maximum value here. Nearly it will be somewhere in 33-34 degree angle of attack. But in this you are going to get quite less amount of lift coefficient, nearly 1.1. So at alpha is equal to 0 degree, the CL max you are going to get somewhere 1.1. But if you see the last one, that is plus 15 degree, alpha is equal to plus 15 degree, you are going to get CL max nearly, you can say 1.6. And also, but little this stall angle is somewhat reduced. Previously, in the first case, it was somewhere 35. Now it is nearly 30 degree. So we can see that at alpha is equal to 0, alpha is equal to 0 is here. So it is giving somewhere 1.4. But at alpha is equal to 15 degree plus 15 degree, when the angle of attack is this incidence angle of the horizontal tail is positive 15 degree, we are going to get maximum coefficient of lift, but the stall angle is somewhat reduced. But if you go for the minus 30, alpha is equal to minus, it is not alpha, sorry, it is a IH. Okay, so at IH, so here IH, okay, again I am just, IH is equal to, when you are 0 degree, you will get CL max nearly 1.4. IH is equal to plus 15 degree. CL max you are going to get maximum, it is 1.6, it is highest. And when it is a minus 30 degree, you are going to get least, and it is somewhat 1.1 CL max. Okay, but if you see the stall angle of this thing is reducing. So this is the, so the effect of incidence angle is that as it is increased, the coefficient of lift also increased. If CL reduced, if the IH reduced, CL also reduced. Okay, that is the output of this discussion. Now I am going to discuss further about effect of incidence angle and deflection of elevator on CM versus alpha plot. So here we have two plots. One is CM versus alpha and another is CM versus alpha. In this, we can see that at delta E is equal to 0 and delta E is equal to 5 degree here, and here IH is 0, means incidence angle is 0, and here deflection of elevator is 0. So this thing, just I am drawing here, what is the meaning of incidence angle 0? Means this is it is 0, And if IH is 0, but this is your elevator. So here this elevator also is horizontal in this case. So this is IH, means this angle is horizontal of, this is the tail and this is the elevator. Okay, so at alpha, so this delta H is equal to 0, but here delta E is equal to 0, and another case is plus 5 degree here. But here what happens in this case, delta E is 0, but this is the case 1, delta H also 0 and delta E. So delta E 0 and IH 0. Another case, IH 5. Okay. In this case, IH 5 means it is 5 degree like this, but this is 0 degree, and this is from here to here is 5 degree. This is, so if you make the aircraft like this, so if it is like this, it is 0 and this is the elevator. So either you can make like this, or you can make 0 and deflection like this. Okay, so these are the cases which we have to understand. And in this diagram, we can see that some cases are coming, and in the first diagram, we have to see the effect of IH in 3 cases. One is delta E is equal to minus 5 degree, means deflection of elevator is minus 5 means upward. Delta E is equal to 0 and delta is a 5 degree. So if it is 0 degree, you will get trim here, and if it is negative, then trim will be here, means the angle of attack of the trim is high. But if delta E is positive, the alpha trim will be reduced. That is the benefit of this thing. So here this, we can see that Cm delta E is equal to delta Cm by delta E. So here this, you can see 0.3 minus 0.1 is equal to 0.2, and here minus delta E, minus 5 minus 5. So it is a minus 10. So Cm delta E will be minus 0.02 per degree. So this is the control power of the elevator. Now Cm IH, coefficient of moment, when we deflect the incidence angle of the elevator. So delta Cm by delta H. So here 0.3 minus 0.1. So it is a 0.2, and here minus 5 to plus 5, it is a minus 10. So it is 0.02 per degree. So this is the effect of incidence angle, deflection of the incidence angle of horizontal tail, and here it is the deflection of this elevator. So the positive IH deflection is defined as the leading edge up. So leading edge up means it is like this. It is a positive, and if it is like this, it is a negative. Okay, this is the negative IH and this is the positive IH. The negative increment on the, so that a positive IH deflection produces a negative moment. So if it is a positive like this, and here is your aircraft like this is the wing. So it is a positive, means positive here, it will produce a negative minus pitching moment. As you increase the angle of attack positive, lift will be increased, and this distance from here to here, x into lift, L into x, that much pitching moment L into X will be generated, and this will be anti-clockwise or the negative pitching moment. Positive delta E deflection is defined as the trailing edge down that produces a negative increment of the pitching. Same way, if we increase the positive, this elevator, it will also generate and it will also give in this direction. So, the positive deflection of delta E or positive deflection of IH both will produce the negative pitching moment, which is the necessary requirement for the stability of the aircraft. So now, in the previous diagram, we have seen that CL versus alpha. Now in this, coefficient of moment versus alpha. And in this also, we have the incidence angle, variation of incidence angle from plus 15 to minus 30 degree IH variation is present. So, we can see here that at 0 degree, what is happening? So, it is the triangular one. Here, this you can see. This is the plot for the 0 degree. So, you can see that Cm versus Cm alpha is negative. Okay. So, it is stable. So, at IH 0, the aircraft is stable. But one small problem is here. Here very less, because to have the static stable, Cm naught should be positive and Cm alpha should be negative. But it is positive but very, very small. We don't want this much. We want some sufficient amount of this thing, and also it should be there. So we should apply some, always this negative. You see, this is the 15 and this is the 15 degree. This 15 degree is not fit condition, not good condition. Plus 15 degree angle of this incidence angle is not good because Cm naught is negative. So this is not the requirement for our static stability. Static stability should be positive. So these two cases are not good here. First case, when IH is equal to 0 and when IH is equal to plus 15, this is not required for stability. But if you see the another two cases, minus 15 and the minus 30, this one is a minus 30 and this one is a minus 15 degree of IH. So both are very good, and trimming is also happening at positive angle of attack. Alpha is equal to positive. So, and sufficient positive. Here you see in these two cases, trimming is not there at all. So these two cases means plus 15 and minus 30 incidence angles are required for a stable aircraft. So the negative slope of each curve indicating static longitudinal stability, and also notice that the curve shift upward as IH becomes more negative. So as and when the incidence angle of the horizontal tail becomes negative, the Cm naught becomes positive, and that is the requirement of our aircraft stability. So to have the aircraft static stability, especially the longitudinal static stability, we should fix our horizontal tail in negative direction. Mostly 15 degree will be sufficient, but it should not increase more than 30 degree. So between 15 to 30 degree if you put, it will give a better result, better Cm naught, and alpha trim also will be in the positive direction, so that it is useful for our need. Now I am going to discuss about aircraft aerodynamic center. It is very, very important parameter for studying the aircraft stability and control. And so aircraft aerodynamic center is that point on the aircraft where the variation of aircraft pitching moment coefficient with angle of attack is 0. So this is a very good, a very important point, because it gives the constant value for the pitching moment and angle of attack if we calculate from aerodynamic center. The location of the aerodynamic center is normally defined with respect to the mean chord of the wing using the bar notation. Normally, with respect to a non-dimensional form, we are using the aerodynamic center. So x bar AC, so x AC by c bar, where c bar is a mean aerodynamic chord. To develop an expression for aircraft aerodynamic center, we use the first one, the definition, which says that Cm alpha must be equal to 0. By this definition, here Cm alpha is equal to 0. So this is the definition of aerodynamic center. So first we have to use this equation, and the aircraft aerodynamic center, if aircraft is rotated about the aerodynamic center, and the fact that the CG of the aircraft must be at the aerodynamic center if the aircraft is rotating about the aerodynamic center. So in this, the first case, Cm alpha should be 0, and the second case is x bar CG is equal to x bar AC. Means if this is the CG and this is the AC, so both should be in the one point. So in this two condition, we have to find the aircraft aerodynamic center. Applying these constants, equation 4 below, and solving for the aircraft aerodynamic center, so we can get Cm alpha is equal to CL alpha wing fuselage x bar CG minus x bar AC minus CL alpha H neta H SH by S x bar ACH minus x bar CG 1 minus d epsilon by d alpha. This we have already derived in our 4th or 5th class. This we have already done. So here we have to find out XAC. We are interested to find out aerodynamic center, location of the aerodynamic center. So this XAC is equal to here XAC wing fuselage plus this one here. So we want to plus CL alpha W alpha H by CL alpha WF neta H SHS x bar AH 1 minus d epsilon divided by 1 plus CL alpha H CL alpha WF neta H SH by S 1 minus d epsilon by d alpha. So notice that the aircraft AC may be moved aft on the aircraft by increasing XAH, XACH means it is aerodynamic center of horizontal tail. If you want to, aircraft may be moved aft, AC may be aft on the aircraft by increasing this value here. If we increase this value, XAC will be going aft. Or SH, or you increase SH, area of the horizontal tail, and or CL alpha W, CL alpha H. So either you increase this, either you increase this, either increase these three parameters. If you increase, the X bar AC will be increased, means going backward, going backward. So that is the meaning of this approach can be very useful in designing an aircraft for static stability, as we will see, moving the aircraft aerodynamic center aft will increase the static longitudinal stability, and moving it forward decrease static stability for a given CG location. So if the CG is fixed, if CG is fixed, here CG, and this is 1 and this is 2, AC1 and this is the AC2. So moving the aircraft AC aft will increase the static longitudinal stability. Okay, so as you increase AC here, okay, 1, 2, so as it goes behind, static stability is increased. So that is the importance of this equation. So here a small problem is here. Estimate the location of the aircraft aerodynamics center for the A10 given the following conditions are given. Area of the aircraft wing is given 506 feet square. Area of the horizontal tail is 120 feet square. Neta h is equal to 0.9. Aspect ratio is 6.54. Aspect ratio of the tail is 3.0. D epsilon by D alpha is equal to 0.1. CL alpha is given minus 0.11. C bar is 8.8 feet. XAC is equal to 26.25 feet. So these things are given. So we have to find out the CL alpha WF first. So CL alpha is equal to CL alpha divided by 1 plus 57.3 CL alpha pi EAR. So here we have to, it is given here that CL alpha is given here 0.11, 1 plus 57.3 into 0.11. It is also given pi 3.14. Then A, aspect ratio, E is given here 0.9. This E is NH is 0.9 and aspect ratio is 6.54. This is the wing. So we will get here this 0.082 per degree. This we have got here, and now to find out CL alpha H is equal to 0.11 CL alpha divided by 1 plus 57.3 here we have to put 0.9 and aspect ratio we have to put here 3. Okay, so here we can assume that E is equal to 0.9. Okay, so we got here that CL alpha H, coefficient of lift for horizontal tail is 0.0631 and for the wing is 0.082 per degree. Now we have to find out aerodynamic center, the location of the aerodynamic center. So this aerodynamic center is equal to X bar AC wing fuselage plus CL alpha H CL wing fuselage NH SH by S ACH 1 minus D epsilon by D alpha divided by 1 plus CL alpha H CL alpha wing fuselage neta H SH by S 1 minus D epsilon by D alpha. Everything we know this, all the parameter, this we have find out. Neta we have this SH is 120 and here is S is 5.6. Then X ACH is equal to 2.98. 1 minus 0.1 D epsilon by D alpha is also given. So we got that X bar AC is equal to aerodynamic center location is 0.602. So 0.602 is the location of the aerodynamic center from the leading edge of the aircraft wing. Okay, that is the meaning of this result. Now I am going to go ahead with the some other parameter of the longitudinal static stability. In longitudinal static stability will primarily refer to aircraft pitching moment characteristics and will be analyzed for the stick fixed condition. We are doing the work for stick fixed, where the control movements are not done. All the primary controls, elevator, rudder or ailerons are fixed. They are not moved. The sign of the static derivative, that is Cm alpha, is key in determining the static longitudinal stability of an aircraft. So this Cm alpha is the variation of coefficient of moment with the variation of angle of attack. This parameter is one of the most important parameters, and by this we have to understand whether the system is stable, unstable or neutral stable. The requirement to trim the aircraft at usable angle of attack is also discussed with the longitudinal stability requirement. So not only Cm alpha but Cm naught also is very important, because the trimming angle of attack is also very important. It should be positive trim, means Cm naught should be positive and Cm alpha should be negative. Then only we can say that aircraft is longitudinal static stable. Both are generally necessary to achieve acceptable flight characteristics. So what are the two things? First thing is Cm alpha, it should be negative. The second is Cm naught, it should be positive. These two parameters we have to make sure that it is meeting this requirement. If I draw the plot for this, it should go like this. If it is like this, means this is the Cm naught at 0 and this should be trim at positive angle of attack. At positive angle of attack. This has to be met. Then only we can say that aircraft is statically longitudinal stable. Now we have to discuss about the trim condition of the aircraft, and we should achieve this condition. We can see here a typical diagram where this is the reference line here. Every parameters are measured from this line, reference line. This is the wing, this is the tail, and here we are assuming your engine. So this is the aerodynamic center. So it is XAC wing fuselage. It is represented as a XAC wing fuselage. Here a inherent moment will be there. It is called aerodynamic center, wing fuselage moment. And here aerodynamic center, the lift will be produced. Weight is here. So the center of gravity location is this one. If you see by this diagram, you can see that it is unstable aircraft. It will move in this direction. Okay, so to counter or to have the trim of this moment, we should have one tail, and tail should produce a lift in upward direction. So from here to here, this is called XACH. This from here to here. So this XACH, the effective distance will be from here to here. Okay, so we can write XACH minus XCG. This is the from CG to AC of this. And if you see how much will be this from here to here, XCG minus XAC, XCG minus XAC wing fuselage. So this is this distance. So now requirement for longitudinal trim is that the overall pitching moment acting on the aircraft be equal to 0. Or in coefficient form, if you take in the coefficient form, the lift wing fuselage means this lift into XCG minus XAC, means this lift into this distance plus MACW. These both are in the clockwise direction. Minus this is in anti-clockwise direction. In this direction, anti-clockwise, LH into XAC minus XCG minus T into this distance, T into dt. This is the vertical distance. D into T is equal to 0. The sum of all the moments are now 0. So now we have to find out LH. How much lift is required from the tail? This LH is equal to LW XCG minus XAC plus MACW minus TD divided by XCG XAC minus XCG. This is the distance which we have to divide. So with XCG less than or equal to XACW. If XCG here, this XCG is less than or equal to XACWF. It can be seen that a download LH is less than 0 is needed. So if XCG is less than XACW, so this XCG here, if this XCG is less than XAC, then we need in this direction needed to trim. If XCG is greater than XACW, the load on the horizontal tail may be either up or down on the magnitude of the MACWF. Okay, so this depend upon the MACW. Okay, so these things we can understand that this lift of the tail, it can be positive, it can be negative. This depend upon the different criteria. It is not the one criteria by which we can define that it should be positive or the negative. So now condition for the trim. For a trim condition, the coefficient of moment should be 0. So Cm naught plus Cm alpha into alpha by the Taylor series plus Cm delta E into delta E plus Cm IH is equal to 0. This means all the angle of attack, elevator deflection and the incidence angle, all should be, the sum of these things should be 0. Another requirement for trim is that the ability to trim the aircraft as positive angle of attack. Okay, so this is generally accomplished by Cm naught plus Cm IH should be greater than 0. These two values, Cm naught plus Cm IH and IH should be greater than 0 or positive. So if these things are positive, you will get this thing at positive angle of attack. Otherwise, it will be difficult to get the trim condition. So the primary requirement for the longitudinal static stability is Cm alpha should be negative. The vertical intercept positive so that the aircraft can be trimmed at a positive angle of attack. So this is called the here vertical intercept Cm naught, it should be positive. So if this is condition and Cm alpha should be negative, the slope of this curve, it should be negative. If you are able to make this, then we can say that aircraft is statically stable. The Cm delta E term in Cm equation allows adjustment of the trim angle of attack by varying the elevator deflection delta E as illustrated in the figure below. Elevator required to trim delta E trim is equal to minus Cm naught plus Cm alpha plus Cm IH divided by Cm delta E. So delta E trim is equal to minus Cm naught plus Cm CL plus Cm IH. This we can change to Cm CL into CL. So here you will get that Cm alpha is equal to Cm CL for low angle of attack, as in the equation is linear. So in this way we can find out that it is your delta trim, the trim required, we can calculate by this equation. If we combine Cm0 and Cmih into one term that meets the criteria, so this equation can become that delta E trim is equal to minus Cm0 plus Cmih divided by Cm delta E minus CmCl into Cl trim by Cm delta E. So in simpler form, we can write that delta E trim is equal to delta E naught plus CmCl into Cl trim by Cm delta E, where delta E naught is equal to minus this term. This term is here we have made as a delta E naught. So delta E naught can be thought of as the elevator required to trim the aircraft at a lift coefficient of 0. So when the lift is not produced, that time whatever is delta E is required, that is called delta E requirement. So here this we can see in this diagram, this is the delta E where Cl is 0. So this is the delta E. This much delta E is required to handle this case. Elevator position typically at lower values of lift coefficient at higher speed, positive value of delta E trailing is down or required. Means when the aircraft is flying with a less speed, more delta E is required. This equates to coming forward with the stick. So we have to make stick forward at higher value of lift coefficient, means at lower speeds, negative value of delta E trailing is up are required, which equates to aft. That time we have to put backward. So at higher value of lift. So if you want a higher value of lift, a negative value of delta E are required. Means it should go upward. And if you want this lower value, then it should be put down. So the primary requirement for the longitudinal stability is Cm alpha should be negative, and this requirements provides an aerodynamic restoring moment for angle of attack perturbation to steady state flight. A negative Cm alpha results in a negative slope on Cm versus alpha plot. For a simple vehicle in flight like a projectile, a negative Cm alpha is achieved by simply locating the CG in front of the AC. So if the CG is ahead of the AC, this condition we can get. We can see that an airfoil with negative camber, that is the positive Cm AC, will be able to achieve Cm naught and will also be statically stable if the CG is located in front of the AC. Here is this diagram explanation of the static stability. In this figure, A represents the trimmed condition, B represents the perturbed increased angle of attack, and C represents the decreased angle of attack. So in figure B, when angle of attack is increased, the lift force also increased. As the CG is ahead of the AC, this increase the lift will make the moment which tends the aircraft to go ahead. And here is to have the statically stable plot of Cm versus angle of attack must be negative as shown in this figure. Note again that a negative Cm alpha is required for static stability. So here C, A and B. These are the three cases which are shown, and here also these things are represented. So accordingly, we have to see that it should meet this requirement. So these are the references which I have taken. That is the Yachout, Introduction to Aircraft Flight Mechanics, and then Nelson, Flight Stability and Control. And also I have taken the references from NPTEL lecture of Aircraft Stability and Control by Professor A.K. Ghosh from IIT Kanpur. Thank you very much for joining this class. I will be continuing with the next class. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.